hyperbolas. Hyperbolas are a very similar shape to ellipses in the way they're generated and the information that we gain from them. I'm going to just quickly show you what a hyperbola looks like. And I think most of you probably know already. Let's go there. All right, so that's an example of a hyperbola that is opening left and right. It's opening towards your x-axis. You can have hyperbolas that open up and down like that towards your y-axis. Okay, and we'll talk about how we can determine the difference between the two as we go on today. But I want to first just kind of introduce everything with that original one that I had on here that I messed up. Just want to talk about some maybe physical properties that exist for hyperbolas. Okay. We talked about on an ellipse that if we take a point on the ellipse and then trace back to both foci, okay, we should be able to add those two distances, and that distance is always the same no matter where that point on the ellipse goes, right? Okay. Well, let's kind of work through that same similar idea, but now do it for a hyperbola. Okay. So I do want to show you the algebra stuff here. I'm going to put a point, doesn't matter where it goes, I'm going to put the point D on my hyperbola, and now I'm going to trace back from that point to that focus, and then to that focus. Okay? And you see the lengths over here, right? Okay? Add those lengths together, you get like 10.04, correct? I'm going to move D. I add those together, 12.1. Is that the same value that I had before? No. So we're seeing that the sum is no longer the same, right? But if I go back to that, subtract those two numbers. What do you get? 4. Subtract those two numbers, what do you get? 4. Subtract those two numbers, what do you get? Okay, so what are we seeing? That a hyperbola is the locus of points, or the set of all points, in which the difference between a point on the hyperbola and the length from that point to one focus minus the length from the point to the other focus, that difference is always constant. Okay? Yesterday in ellipse we said the sum was constant, right? In a hyperbola, the difference is constant. Okay? And that's what creates the hyperbola. Is that all right? Okay. I want to talk about another before we get into so that's the geometric definition. Okay. I want to talk about some some algebraic connections and physical connections with hyperbolas, which becomes very useful and it really is similar to maybe what we know about parabolas. So let me open a window here. if you guys remember, we haven't talked about how parabolas and conic section kind of relate, and how we develop what we call a focus and what we get when we call we get directrix. But you have maybe seen those things last year in Algebra 2. Essentially, the focus and the directrix are linked together. What I want you guys to kind of know physically about parabolas. I'll get this thing out of the way. There we go. And I think we talked a little bit about this yesterday when we talked about like people standing on the sidelines of NFL games or soccer games that have those kind of shields. Okay, those shields are parabolic. They're usually called parabolic microphones or parabolic lenses. What happens is that we can take sound waves. We take electromagnetic waves. Maybe we're talking about like a satellite dish on your house or something like that, and talking about the transmission waves that are sent off, and your satellite then picks up those transmission waves and then transfers them so that you can see a picture on your TV, right? There's a lot more math and physics involved in that that I don't really want to get into. But your satellite dish on your house, or the satellite dish, or the parabolic microphone that somebody's using on the sideline of a sports event, uses this physical application of parabolas. What happens with parabolas is that when I take, let's say, a transmission wave from the TV station, okay, that travels through space. Electromagnetic waves travel through space, kind of like that. Okay, we'll talk about sine, cosine waves eventually. Maybe you guys have talked about light waves and stuff like that in physics. They'll travel kind of the same way. What's going to happen is that wave is going to bounce off of that parabolic lens or parabolic dish, okay? And when it bounces off that, it's going to get redirected to that point right there. And no matter where, because we've got an infinite number of waves coming in, right? And no matter where they hit that dish, they're always going to get redirected and focused back onto the focus. Does that make sense? Okay. So my satellite dish, if you guys ever seen a satellite dish on your house, you looked at it, a lot of times it's going to be a very rough picture. So there's my dish, and you've got some spokes that come off, and there's a little thingy right there, right? Well, that thingy is like a receiver, correct? Okay. And it is picking up, it's located at the focus of the parabola, okay, of that dish, and it's just being able to pick up and translate those waves. Does that make sense? Into a signal that then you can see on your TV. Okay. People on sidelines of the sporting events, okay, what's at the focus of their dish? Microphone. Okay, they're trying to pick up sound, right? Okay. So they want all those sound waves to be refocused on the microphone, and then it gives you a better experience at home, right? Okay. So that is also used a lot with, like I said, light waves in regards to telescopes. A lot of telescopes use parabolic lenses, okay, because we're trying to collect as much light as we can and focus it on a central point, right? So we can see the image. There's a lot of math and physics that go into telescopes, and I don't know all that stuff, but kind of in a general concept, we're using hyperbolas and parabolas. Now, why do I talk about that? Because when I talk about hyperbolas, there's a very similar concept occurring with hyperbolas. What happens with hyperbola, I'm just get rid of these axes, I'll get rid of my grid. If I take, let's just say, a beam of light, okay, or a laser or whatever, and I focus that beam of light from anywhere I want to, okay, I focus it on that focus right there. What's going to happen is that when it hits this hyperbola, it's going to bounce off, and it's going to come back to that focus right there. Does that make sense? Beam of light on that. It's going to hit my hyperbola, and it's going to be redirected. Oh, it's going to be redirected from there back to there. Mouse is a little sticky. I don't know what's going on. Did you get the idea, right? So we go light directed on A, hits my hyperbola, and bounces back to that focus. So what happens is if you direct a beam of light on one focus, it will bounce off, it will reflect off the hyperbola, and redirect itself onto the other focus. Okay? And that physical relationship is used a lot in trying to take light and make light kind of reflect back and forth inside telescopes to create a larger, clearer image. Is that okay with everybody? Okay. You know, a lot of times, and like I said, I don't know a lot about telescopes, but you know, the higher power telescopes, they're not very long, are they? But they're really fat, aren't they? Okay. And that has to do with the lenses and the hyperbolic shape of those lenses to kind of redirect that light. All right, so how do we come up with the equation of a hyperbola? It's very similar to that of a ellipse, okay? And the fact that we're going to have some quantity squared. And I'm actually going to write it this way. Let's go x minus h. That quantity squared. Where h is the x coordinate of our center. Okay, in the last example we did, that x coordinate was 0. We'll have that over some a squared, and again, we're going to have a squared and b squared in our denominators. And again, I don't care which one's which. Okay, you might see a b here instead of an a. It doesn't matter. You're still going to have over here y minus k, quantity squared. On the bottom, you're going to have some b squared. And that equals 1. Again, like I said, that could be b squared and this could be a squared. Does not matter. But instead of adding, because addition was the ellipse, right? And we knew it was addition with an ellipse because that was similar to a circle. An ellipse is just an elongated circle, right? With a hyperbola, it's going to be a what? It's going to be a minus sign. Okay? Maybe another way for you to remember, if you remember the definition, the geometric definition of these things, on ellipse, you're adding those distances, and that sum is always constant, right? Okay? So then in the formula, it's adding. With a hyperbola, you're subtracting those distances from the point to the focus, okay? So in the formula, or the equation, that's subtraction, okay? So there's a lot of different maybe relationships that you can use to help you remember. That's got to be a minus sign in this case. What is nice on the final in this course, you will have a reference sheet, and this will be on the reference sheet. Okay. H and K, like I said, H and K are the center. Last one we did, the center was at 0, 0. So it might be good to write that is the center again. Now we did talk about how some of these can open up and down. Some of them open left and right. The way I have this one positioned right now, that one is going to open because the x value comes first in the whole expression, the whole equation. That hyperbola is going to open that way. Okay? If x comes first, essentially your x-axis is going to be on the interior of your hyperbolic branches. We call those branches when we talk about those curves. Is that okay? So that's important to understand because we should know that subtraction if I do this, actually, should still be K. Are these two things the same? Is 2 minus 3 the same thing as 3 minus 2? No. Okay. So we know subtraction is not commutative. So when I rewrite these, when I reorder, essentially putting this expression first and this expression second, the order of subtraction matters. So now with this situation, what we would have is parabolas that are, or sorry, not parabolas, hyperbolas that are opening up and down. Okay. Now, how do we remember this? How do we know visually from the equation whether we open left or right, or if we open up or down? And it's that first variable. Okay. As you look at it, you've already distinguished, when you go through these, the first thing you want to distinguish, is it a plus sign or a minus sign that's in the middle? So that tells me ellipse or hyperbola. We've already established these things on hyperbola, so then we instantly look at that variable in the first location, and if it's an x, it tells you that your hyperbola opens up to that axis. It has that axis on the inside of it. If it's a y, it tells you that your hyperbola is opening to the y-axis, or it has the y-axis inside it. Okay? Okay. Now we can move these things around from 0, 0, and all that kind of stuff as well, and it's the same procedure that we did with ellipses. Okay, if I want to move it to the right, I simply subtract something from x. If I want to move it down, I would maybe add something to my y. Okay, so we can do the whole repositioning process the same. All right, so let's do an example of this. Let's show you how we graph these things. I'm just going to go x squared over 16 minus y squared over 9 is equal to 1. So we instantly know this thing's going to be a hyperbola because of the subtraction sign in the middle. Okay? And we instantly know, because the x variable comes first, that this thing is opening left and right. Okay? So I always kind of, on the side, or just make a mental note that this thing is eventually going to look kind of like that. Okay? Just forcing myself to know that is, I think, very useful. All right, now the next thing. It's the exact same procedure that we used when we dealt with ellipses. You're going to take that number right there. And when we dealt with ellipses, we took the square root of it, right? So let's take the square root of it again. It gives you what? 4. Okay? So, and it's paired with the x, right? So on that horizontal axis, I'm going to move 4 units away from my center. Well, right now we know our center is at 0, 0. So I'm going to use 4 units to the left. 1, 2, 3, 4. And I'm going to go 4 units to the right. 1, 2, 3, 4. All right. So what is nice about that is that we have now figured out where the vertex, essentially, of those branches of the hyperbola come down and touch, essentially, the x-axis. Okay, or cross the x-axis. All right. So I know that, looking back over at this picture here, that point right there would be at -4. That point right there would be at +4. Is that okay with everybody? That's what that just told us. I'm going to look at this number here. I'm going to take the square root of it. Okay? And that's going to tell me to go from my center up 3 units. So we get that. And I get that. Okay? Now we're going to do something that's going to help us develop kind of the end behavior of these hyperbolas. Because right now, we've only got essentially that point and that point of an infinite number of points on my curve. And that's really not enough to graph it. So what we do, and this works every time, is that we're going to take a horizontal line through 3 a horizontal line through -3, a vertical line through -4, and a vertical line through 4. Okay, so those initial points that we found, our initial coordinates, we then create respective horizontal and vertical lines through them. Okay. Now the reason we do that is because when we connect that vertex of that, you always create a rectangle here. When you connect that vertex with that vertex of your rectangle and extend that as a line that continues on forever, we have now created an asymptote for our hyperbola that will show us the end behavior of our hyperbola. Okay? So I'm going to color that red. Then we do the exact same thing with the other diagonal. Okay? We now know that this thing opens left and right, correct? We know it's going to have that point there and have that point there. And as I move to the right, I'm going to approach that asymptote and that asymptote. And then as I move to the left, that asymptote and that asymptote. So that black curve then, those two black branches are our hyperbola. Is that something we can do? Okay. Now they're going to ask you to do some other things, like find the location of the focus, okay, or both focus. And it's also going to ask you to find the equation of those asymptotes. Okay. And if you go back to yesterday on the PowerPoint, I gave you a kind of a blue box of a bunch of formulas for ellipses, and I told you that's what you saw probably last year or any Algebra 2 course. But there's a lot of stuff there that you can get mixed up, right? Well, hyperbolas have the same blue box in another PowerPoint that is very similar, but has even more things in it because you got these asymptotes, okay? And they give you formulas for finding those asymptotes, and the asymptotes relate to these values here. They're the essentially a y equals like b over a, and y equals the opposite of b over a, and a over b, and that kind of stuff. And it gets very muddled and cluttered, and a lot of stuff that gets confusing. But if you make this box, you can find the equation of this line pretty easy. Y equals, goes through a y-intercept of 0, right? Okay, so my b value is 0, and my slope is up 3 over 4, right? So the equation of this is 3/4 x. Which if you were looking on like a PowerPoint or researching this stuff, they would say, if this is, that's A and that's B, they're going to say one of your equations is, if this is A squared and that's B squared, one of your equations for an asymptote will say it's y equals B over A. Does that make sense? Okay. I think that's too much to learn, too much to deal with and memorize. You can make that box. You can develop the slope of that line pretty easily and come up with the equation. What's the slope of this one going to be? Okay, it's going to be the opposite. So it's just going to be y equals -3/4 x as the equation of that asymptote. And then those are oblique or slant asymptotes. So as we move to the right on our hyperbola and we move to the left on our hyperbola, these y values will approximate and eventually end up being the same as these y values. Okay. The next thing we want to do is find where the focus location should be. And in either branch, your focus is going to be on the inside of your hyperbola. Okay? And that's something to remember just in case you mess your formula. Okay? Yesterday we had a formula for ellipses where we made that subtraction, right? For hyperbolas, it is addition. So now, c squared would be, 16 plus 9 is going to be 25, right? So c is equal to root 25, which is just 5. Now remember c, what c is the distance from your center to one of your focus. I don't know if it's foci, focus, focuses. I don't know how to say focus. Is it foci or foci? Foci. I think it's foci. I want to look. So we've got that length of 5, right? I'm going to go from my center, and I know my focus should be on the inside of my branch. Okay? So I know to go to the right. I don't go up, right? Because you got options. So I need to go to the right. So you go 1, 2, 3, 4, 5, and right there is a focus. At 5, 0. We do the same thing over here. Go 5 in the negative direction, and there's my other focus. Okay? What would happen if I subtracted on accident in this formula? I would get what, radical 7? Radical 7 is about 2.6, I believe. Where would 2.6 be? Be right there, right? Is that a problem? Yeah, our focus has to be on the inside of the hyperbola, right? Okay? So those little relationships can help you maybe realize whether you've used the correct formula to find the location of your focus. Okay? Knowing that on an ellipse, the focus always has to be on the inside of the ellipse. On a hyperbola, the focus always has to be on the inside of the branches. Can help you realize that c squared equals a squared plus b squared, or c squared equals a squared minus b squared, whether you've done it correctly or not. Okay? Remembering that distance always has to be positive, so in the event that you do subtract them in the ellipse, you know, make sure that you're subtracting them in the correct order. Does it matter there which, and this is another reason why I don't care which denominator is a squared and which denominator is b squared, because does it matter whether I add those as a squared plus b squared or b squared plus a squared? No. Okay, so it doesn't matter because addition is commutative. So there's no reason to know which one's which or care which one's which. And the only reason that we would need to know maybe which one's which up here is to realize that which direction the hyperbola opens up. But we've already talked about what variable comes first is the direction it's opening up, right? And then that's going to tell you the length in the x direction. That's going to tell you the length in the y direction for your box. Set that box up, you've got your equations. I just think that process, once you do that a couple times, it's so much easier and safer in regards to memorization of all the different formulas and additional criteria that maybe the PowerPoints provide you, or maybe what you've seen in a textbook or something like that. Does that kind of make sense? I think this is a great place to explain kind of theoretically, how maybe you should approach mathematics. Okay, don't try to memorize things. Okay, if you can develop relationships, it's so much easier to understand concepts and remember them for the long run in regards to, or in comparison to, memorization. You're going to find that out to be true a lot in trig when we get to that stuff as well after next week. Relationships are a huge aspect of trig. And I think you guys that are in physics are going to start to realize that a lot of things that you've done in physics so far is simply just what you do in trigonometry. It's SOHCAHTOA. Okay? Now the formulas in physics are set up in a manner in which you don't recognize right away that's SOHCAHTOA, but that's all it is. Okay? So those of you that have done some physics stuff, I think your eyes are going to be opened a little bit when we get to trig. Okay? But it's all about relationships. It's all about understanding those relationships and not trying to memorize things. Okay? You try to memorize things, you're going to mess things up. I will